useful is that we can apply a magnetic field to the single crystal samples and then measure the inelastic excitations as a function of field. And as you see here, if you apply a small field of 0.25 Tesla, you start to lift up this diffuse scattering, and it starts to organize itself into these sharp spin wave excitations. So this is a signature that we're entering a field polarized state. And if you go to high enough fields, you can imagine that this could be well described by linear spin wave theory, which is what we did. So working with Leon Valent and Lucille Fabry, we were able to fit our data to this anisotropic exchange model. And you can see here we did this for 2 field strengths. And let me point out that the field was along one direction, 1 bar 0. And we chose this G-tensor in order to model the spin waves with. This was actually extracted from a crystal electric field calculation. And so doing this, we came up with a nice comparison with the 5 Tesla and 2 Tesla data, and we're able to robustly conclude that we had these 4 exchange parameters, the largest one being this JZZ, which, as you see here, is the largest and is ferromagnetic, which is, in fact, what you'd expect for a spinite. So if these other terms were not present, you could say that you had a classical spinite. So you might expect to have monopoles arising from spin flips in that type of scenario. Now, these other exchange parameters, which are smaller, but as you see here, not tiny, right? So this is the same order of magnitude. These could potentially be thought of as introducing quantum fluctuations into a spinite model. And from that, you would have not just the monopoles, but you'd have emergent electrodynamics. So you would also have emergent photons and emergent electrons, which would be extremely exciting. So if you take those parameters and try to understand what the ground state is, this was done by Leon and Lucille, and they did this using something called gauge mean field theory. What they found is that for large JZZ, there's 4 phases in the phase diagram, 2 of which are exotic. One of them is the quantum spin liquid, which supports this emergent electrodynamics with the photons, monopoles, and electrons. And then there's another interesting phase here, the Coulomb ferromagnet, which is a partially polarized phase that's related to this quantum spin liquid. So it has the same quasi-particle excitation, but it has a partially ordered moment. And then these other 2 phases are more conventionally ordered phases of ferromagnet and then anti-ferromagnet. And so, depending on where exactly these phase boundaries are, keep in mind this is the type of mean field theory, so that these could be shifted around a little bit. You could think that ytterbium titanate might be close to some of these phase boundaries, which may explain why it's so sensitive to disorder. Furthermore, recently there's been some very nice work by 2 other groups who have come up with another alternative set of parameters, actually 2 different sets of parameters, but they're close to one another, which indicates that ytterbium titanate may lie close to a classical phase boundary between this displayed ferromagnetic state and these 2 anti-ferromagnetic phases, psi 2 and psi 3. And so in this scenario, this would also be a case in which we're lying close to a phase boundary and having the influence of perhaps strong quantum fluctuations because of that lying close to that boundary. And so one question is, what role does the known sample dependence play in where we are in these various phase diagrams? So let me focus on 2 of the powders, or 2 of the ytterbium titanate samples that were made at McMaster University. One of them is the single crystal that I've been telling you about. This was grown by the floating zone method. And the other is a powder sample, which was never grown as a single crystal. So this was purely solid state, never been melted. And as you can see here, this is a log scale, there's quite a big difference between these two curves. But I think it's perhaps relevant to show this on a linear scale. We're used to looking at it as a log scale, but on a linear scale, you can see the powder is several orders of magnitude higher in the peak sharpness and therefore the height of the peak. And so I don't think you could argue that this is a second order phase transition. This is definitely first order, and also I don't think you could argue that they have the same purity, the two samples. And another thing that's interesting is that although to some extent the height of this peak depends on how you measure it, so what type of specific heat measurement you do, the single crystals have only ever reached, say, about 8 joules per Kelvin per mole. And this is, quite a big difference between the powders and the crystals. So what causes this difference was the question that we had. And in order to address this, we actually grew a single crystal and then crushed it up. And we crushed it up so that we could compare to a powder sample that had never been grown as a single crystal. And then undertook a fairly careful crystallography study in which we compared the diffraction patterns at 15 kelvin, this is in a non-magnetic state, between the two samples. And what we were able to conclude is that the powder sample, which had never been grown as a crystal, has a 0% stuffing, and the single crystals that have been crushed up have about 2.3% stuffing. Okay, so what is stuffing? Stuffing is you take an terbium ion, an extra one, and put it on the titanium 4+ sublattice, which is supposed to be non-magnetic. So for those of you familiar with Herbert-Smithite, this is sort of similar to the case with Herbert-Smithite, where you have extra magnetic ions off of the sublattice that you're interested in, and you're not disrupting the connectivity of the actual particle lattice. So we don't have titanium going back onto the ytterbium site. We only have ytterbium going on to the titanium site. And this is one of the ways that you can have disorder in these floating zone crystals. So how you can determine that you have this stuffing is by looking very carefully at certain peaks, relative peak heights. So here, the stoichiometric powder, you have a sort of a lower 222 peak compared to a 311 peak. And then in the crushed single crystal, you see that these peak intensities are almost equal. So that among other peaks in this pattern, tell you sort of about the level of stuffing in your sample. So the question is, in the stoichiometric samples, which are the powder samples, what is the ground state, or what are the magnetic ground state properties? Okay, so that's what the point of this talk is. I think I have enough time. Okay, so we did 2 different neutron scattering measurements on the exact same stoichiometric powder that I just showed you the diffraction from. And in order to make sure that the powder gets cold below 1 Kelvin, it's important to take certain measures. And one of them is you want to use a copper can, and you want to fill it with about 10 atmospheres of helium gas at room temperature. This allows, once the helium goes through a superfluid transition, it allows the superfluid helium to coat the grain of powder, which actually performs the heat transfer from the copper can. And so without doing this, we know that you won't be able to actually see the signature that we were able to see. And so we did one experiment on the SPINS triple axis spectrometer at NIST, and that was to measure the elastic scattering in this powder. And then we did another experiment on the disc chopper spectrometer at NIST, using exactly the same can. In fact, we didn't open it after the experiment, so should be exactly the same temperature stability. And let me first show you the elastic scattering. So this is elastic to within plus or minus 0.25 milli-electron volts, which may be an important thing to consider, considering that there is a fair amount of diffuse scattering that we know extends up to about 0.6 milli-electron volts. but within this